Hi everyone, geophysicist Stefan Burns here, and today we're going to dive into the realm of magnetic anomalies. Now there are a bunch of very interesting magnetic anomalies found across our planet. We'll discuss many of these in depth in today's video, and they are linked to a bunch of different phenomenon. For example, magnetic anomalies can be created from impact events, from small to large. They also can be created from extensive volcanism, and they may even provide us a way to find ancient and lost civilizations. So for example, we have the Bengui magnetic anomaly here located in Central Africa. This is very potentially related to a massive impact that occurred back in the Precambrian more than 500 million years ago. We also have the Richat structure, which is located in a very notable magnetic anomaly. There is the South Atlantic anomaly, which we will discuss, a very interesting, potentially huge impact magnetic anomaly located in North America, and lots of overall magnetic anomalies distributed across North America, and much more. So we will discuss all of that, but we will start with what is a magnetic anomaly. Then we will look at the plasmasphere of our planet, which creates temporary magnetic anomalies during things like geomagnetic storms. And we'll discuss the South Atlantic anomaly before going into these near surface magnetic anomalies that are created from impact events, volcanism, and more. We'll begin with a quick overview of what are magnetic anomalies in the first place. And to do this, we have to learn a little bit about the Earth and the fact that it has a magnetic field. So the Earth is like a bar magnet in many ways, just like the one that you find on a refrigerator. It has this magnetic field, and it's generated in the core, goes through the mantle, and then out through the crust. So you can see the magnetic field here, the generation, and how the magnetic field changes across space, and it also changes across time, which we will discuss shortly. So the Earth has this internally sustaining magnetic field strong enough to propagate through all the geologic material of the mantle, of the crust, and reach the surface, go out to space. And some materials have intrinsic magnetic field properties. One example is magnetite Fe3O4. It is ferromagnetic. It has all of its magnetic domains aligned in the same direction. Their electron spins are all going in the same direction, which gives it a magnetic field and a magnetic force. So when you have magnetite and magnetite containing ore bodies and overall igneous rocks on the surface, they can alter Earth's magnetic field in a certain way. There's something called remnant magnetization, and so this is one of the main ways that magnetic anomalies are created. So yes, igneous rocks contain abundant iron, especially magnetite, and this alters the expression of Earth's magnetic field at the surface. Now, at the surface of the planet, 90% of the magnetic field comes from this internal dipole, which is created from a dynamo action, also potentially a geothermal nuclear reactor, could be both. And so it propagates out. And then on most places of the planet, less than 1% of the magnetic field expression of where you are is related to anomalous features found at the surface. But in certain spots, it is much, much stronger. So we will discuss that. And the other thing that creates magnetic anomalies can be electric currents. When you have an electric current, this creates a magnetic field, either of a direct current, so a static field, or if it's an alternating current, it creates a pulsed magnetic field. And magnetic anomalies can result from geomagnetic storms when there is solar wind and space weather affecting Earth's magnetic field. It changes the plasmasphere, creating these counter magnetic fields to Earth, and this generates magnetic anomalies. So we will learn a little bit about that next. Earth's magnetic field is strongest in the core, but extends way out into space until eventually merges into the interplanetary magnetic field. So within Earth's magnetic field, we have the plasmasphere. A lot of different plasma ions are contained within Earth's magnetic field, and they can change location and create these flows and these currents depending on various factors like space weather. So when you have strong movements of plasma within the plasmasphere, you can change Earth's magnetic field temporarily in terms of its strength and its overall shape and size. So we have, for example, the radiation belts. Here they're charged. Here you can see that they're they're decharged, they have a low flux, and this will alter the magnetic field at the surface of the planet. Specifically at the South Atlantic Anomaly, these radiation belts actually dip really deeply into the ionosphere to an altitude of about 200 kilometers. That weakens Earth's magnetic field. We'll discuss that more in depth in the next one. We also have the ring current, which flows around the planet. This is an equatorial current of electrons, but mostly protons. And this serves to weaken Earth's magnetic field at the equator, because this electric current from the ring current, it creates an oppositional magnetic field. But this is not necessarily an anomaly, typically because it is sustained, but during a geomagnetic storm, the ring current can become enhanced and create an anomalous magnetic anomaly and reduce the field strength in an anomalous way over the span of, let's say, 12 to 24 to 48 hours. But the biggest magnetic anomaly that we have on our planet is related to these plasmasphere dynamics and the radiation belts, and that is the South Atlantic Anomaly. So here we have the South Atlantic Anomaly. You can see here how the field strength is so much lower than the rest of the planet. We have our scale bar down there. And the South Atlantic Anomaly is created from a variety of things working together, but one of the main ones is the fact that the radiation belts here dip deeply down into Earth's atmosphere, all the way down to the ionosphere, and then as a result, those electric currents are happening in the radiation belts. They pull away from the normal magnetic field strength. They create these oppositional magnetic fields. So you can see here radiation striking the Earth. This is actually radiation impacts as recorded by the swarm satellites. And you see just how much radiation funnels down into the South Atlantic Anomaly versus the rest of the planet. Typically, these types of charged particles will flow down through the polar cusp down the field lines, but you have this open area of magnetic flux that also allows these radiation particles like protons to stream in. And so you see a massive amount of energy coming in at the South Atlantic Anomaly, and all those charged particles create those electric currents, which create those oppositional magnetic fields. So there's also odd things happening at the core mantle boundary and within the core that are related to the South Atlantic Anomaly, but it's also in many ways related to the radiation belts. In general, it's an area of open flux for the planet. And so the magnetic field is greatly reduced here. You can see that centered primarily over Brazil, specifically like Rio de Janeiro is right in the center of this South Atlantic Anomaly in many ways. And if you've ever been there, it really has a different type of energy and charge to it. So sometimes you can even feel these types of magnetic anomalies if they're strong enough, and the South Atlantic Anomaly certainly is one of those places. Now we're going to get into the really fun stuff, which are these surface magnetic anomalies. These are connected to a bunch of interesting things that have happened on our planet. We see a few of them right here with this global surface magnetic anomaly map. We'll be looking at a few different versions of this map. One thing to keep in mind is that it's difficult to take all this magnetic data that we have and to combine it into a comprehensive uniform map, because magnetic data can be collected at different altitudes, and that influences the strength of the magnetic data that's collected, because Earth's magnetic field weakens with distance away from the surface. So if you're flying a plane at, let's say, 1 kilometer up, that magnetic field data will be much stronger than a satellite passing over at 350 kilometers. So it's difficult to get all this magnetic field data combined in a way that is scientifically rigorous. Now this data here was collected from the MagSat, which was a satellite that was launched a couple decades ago, and it was flying around about 350 kilometers up in the ionosphere, collected a bunch of magnetic data. Here we see the Bengui magnetic anomaly. We see that magnetic anomaly associated with the Richat structure. We also see the extreme, very large magnetic anomalies that are distributed across North America. We'll talk about that North American craton. Really big magnetic anomaly that we see here in Europe, separating Central Europe from Eastern Europe. We will talk about that as well. And there's some other magnetic anomalies that are distributed across the surface. Antarctica has a few. Fortunately, we won't be able to get to every single magnetic anomaly in this video, but you will see that in general, there is quite a bit of magnetic anomalies on the continents, and then the oceanic crust typically does not have these strong magnetic anomalies because it's always being generated, it's thin, and the areas that have the biggest magnetic anomalies typically are the areas where the continental crust is very, very thick. So we'll talk about that and more. I just wanted to give you this overview map here. We also have some magnetic anomalies in Australia. So yeah, they're all across the planet, and a lot of them have not been explored in depth. So there's a lot that we don't know about these magnetic anomalies, their origin. Here's the Bengui magnetic anomaly as shown with this global magnetic anomaly map created from that MagSat data. We also see that magnetic anomaly here in Western Africa associated with the Richat structure. We will talk about that next. But this anomaly here is very, very interesting. If you look at topographic data, there is a double ring structure found directly over this magnetic anomaly, and there's also a gravity anomaly in this location. So the rule in geophysics generally is that you need 2 or 3 different methods combined that are suggesting the same thing for this to be taken seriously. So you need a magnetic anomaly, and let's say also a gravity anomaly. And then we also here have the elevation and the topographic geomorphology anomaly. So this suggests that there was a very large impact event that occurred more than 600 million years ago back in the Precambrian, and this was so large that that magnetization effect is still in effect today. It hasn't gone away. So the Bengui magnetic anomaly is one of the most impressive on the Earth, by far the largest in Africa, and the best evidence suggests that it is either a large impact structure from early in the history of the Earth or is related to extensive volcanism that intruded up underneath the continental plate and then cooled and stayed there. That's another possibility for this. But overall, it has such a long wavelength characteristic. We can see here, it's this very large wavelength anomaly that suggests it has a very, very deep origin. And that's also very powerful because you get shorter wavelengths typically are higher in amplitude. And so for a long period wave to be even higher amplitude than any short wave anomalies suggests that it is a very large, very deep anomaly. There's also this gravity anomaly that was discussed, this double ring structure. They're all centered together. And if this identification is correct, in this diameter, which is greater than 800 kilometers wide, this implies that the Earth was hit by a very large body, creating by far the largest impact feature found on Earth thus far. The diameter of this impactor would have been from about 80 kilometers to 200 kilometers in diameter. So very, very large. And of course, the early solar system is formed a lot of iron meteorites. These have ferromagnetic material, so this impactor going in could also then create remnant and shock magnetization, but then that magnetic body itself would sink down into the Earth. And perhaps with the Bengui magnetic anomaly, it did not continue sinking all the way to the core, or some of it got spread out and some of it then did sink all the way to the core of the planet. On both sides, we have 4 examples of impact magnetic anomalies. You can see the scale bars here. This is 10 kilometers wide, 50 kilometers wide, 30, and then 15. Here are the nanotesla scales. And some of these are very, very significant. For example, the Manicouagan impact anomaly has a nanotesla rating here that goes beyond 4,000 nanotesla at the top and negative 2,000 nanotesla at the bottom there. So you see this very strong dipole where there's a nearly 6,000 nanotesla swing in the center of this impact crater, which you can see here. This is located in Canada. You can actually see this really easily on Google Earth. There's a lake. So in this area of the planet, like right there, the magnetic field is heavily distorted by this impact anomaly. So this is altering Earth's normal magnetic field heavily right at the center of this impact. Others are smaller. Here we see that the nanotesla scale is just in the hundreds range for this impact. This is a smaller impact there. You can see it's more located in the center. And then for this impact here, we see it's a pretty large scale rating too. This is up to 1200. This is a little bit greater on the negative side, and same deal here. So these can be very strong localized magnetic field disturbances as a result of these impacts. Large impacts create remnant magnetic effects, and what happens is the center of an impact melts and acquires a thermal remnant magnetization. When you have geological materials, when they melt beyond their Curie point, they lose all magnetization, and then when they cool again, especially if they're volcanic in origin or they have a lot of iron-bearing materials, they will then remagnetize to the direction of whatever the magnetic field is. And this is called remnant magnetization. So if you have an impact 50 million years ago that melts something and creates this remnant magnetization, it will hold that magnetic field imprint from 50 million years ago into the present day if it still exists. And then the surrounding area for a very large impact can even acquire shock remnant magnetization. So a very similar mechanism. The stability of remnants is greater for higher pressure events. So generally larger impacts create stronger magnetic anomalies. And shock remnants from a large impact can survive for a very long geologic time. For example, the Bengui magnetic anomaly is expected to be from this impact that was more than 600 million years ago. It's in the Precambrian. So that is very, very old, and yet we still measure it's the largest magnetic anomaly found in Africa. You see here, it has the central positive of magnetic anomaly of about 2000 nanotesla. This is at a flight height of 300 meters, so it's even stronger at the surface. So very, very powerful. And based on early lunar impact records, if we talk about Earth in deep geologic history, there should have been more than 100 impacts from large bodies with diameters greater than 100 kilometers. This is how the Earth was formed. It was just by a whole bunch of things colliding together. This is our best theory for the formation of our planet. And then smaller planetesimals that were about 50 kilometers in diameter were still hitting Earth in the early Precambrian. So a bunch of impact anomalies are found across the planet. A lot of impact anomalies haven't been identified yet. We're still getting these magnetic field maps collected and combined and everything. And the higher quality that we make, the more of these types of structures are being found in them. So we'll look at one in particular for North America at the 4-state area, which is very interesting. That I saw in the data that I haven't read anyone discuss about, so maybe this is something that's new. But first, let's look at the Richat structure in Western Africa, the Eye of the Sahara, which is connected to the lost ancient civilization of Atlantis, and look at the magnetic anomaly there. Here's Google Earth where I layered in surface magnetic field anomaly data. There's the Bengui magnetic anomaly. We can see how large this magnetic anomaly in Western Africa is in comparison. It's quite notable. And if we zoom in, we'll see the Richat structure there, located pretty close to the center of that magnetic anomaly. Now, if you're not familiar with the Richat structure, this is called the Eye of the Sahara, and it is connected to, for many people, the lost city of Atlantis, because it has this ring structure. It in general fits Plato's description. It's fairly close to the Mediterranean. And back when Atlantis was around, the Sahara was green. But we see that the Richat structure here is located within this very notable magnetic anomaly. So there's a lot that we need to learn and explore with some of these magnetic anomalies that are found on the surface. And that Richat structure also has that distinctive impact type of topography. So the Richat structure could be created from an impact event. That seems likely, but we also see this magnetic anomaly located in the same area. Also some pretty strong iron deposits there. Very, very dark. They show up on Google Earth as very, very dark iron ore deposits. But this Richat structure, which many people believe is connected to Atlantis, is located at this magnetic anomaly. So very, very interesting. I wanted to show you that. Now let's look at some of the magnetic anomalies for North America, where we find a potentially even larger impact anomaly in the four-state area. Here we have two different maps for North America. We have the surface magnetic anomaly map, and we also have a very basic geologic map showing the North American craton, the deformed craton, then also the accretionary belt. And this is created from subduction and the Pacific, the North American plate, basically coming together and accreting a bunch of geologic material to it over the last 600 million years. But this main North American craton has been stable for more than 600 million years now. It is very, very thick. It's like 50, 60 kilometers thick. And so it has a very strong remnant magnetization to it that is very, very old and from deep geologic time. So we see that here with our magnetic anomaly map. Here are scale bars. We have the scale for offshore, which is all this right here. And then we also have the land scale there. And so you can see that just in general, the magnetic swings in this craton are much larger than for, like, example, these other spots here and like Alaska and such. They're more in the mid-range with the colors. So you can see just how well the two compare. But what you will notice is that there is a potential ring structure right here in the four-state area. And we're going to zoom in on that. And you even see that central magnetic anomaly there. And it's also located right in this deformed craton. So here's the four-state area. It actually shows up on this map. It's centered basically right there in that deformed section. So could this be related to a massive impact event that occurred in deep geologic time so long ago that there's no notable surface geology that shows us it's sunk down at depth, but these long period magnetic anomaly wavelengths are visible when you collect this data, especially when you're flying at altitude and using satellite data. So this is from the USGS. This map came out in 2002. Let's zoom in on this section here. We'll also look at a magnetic anomaly that's located up there. That's interesting, but let's first zoom in on this four-state potentially impact magnetic anomaly. I first discovered this magnetic anomaly when I was creating this video, and it wasn't from reading any literature or reading about it in a book. It was actually just by looking at the map. I observed that we had that double ring structure and this central magnetic anomaly, like what was seen with other magnetic anomalies I was looking at, like the Bengui and more. And so it's very, very interesting. You see first off this outer ring here, and you can see the magnetic field flux is highest. You can see some of them really follow this ring that I put in, right? This is with Photoshop. And then the second ring there shows up really, really nicely. So you can really see how there is a double ring structure on the magnetics. And then there's even this central magnetic anomaly, pretty central, located right at the junction of these four states. So perhaps this is evidence of an ancient impact event. This would make sense. If we look here, we do have this deformed craton. We talked about how, based on lunar history, there should have been over 100 massive impacts that did occur in the formation of our planet, and then also some very large impacts that occurred afterwards back in like the Precambrian, Cambrian junction. So it is very possible that there is a very, very large impact event that occurred here that's very old and deep in geologic time. And so there's really no surface expression, but we're still seeing the magnetic effects of that because those long period wavelengths are able to reach the surface and be measurable, and even be measurable in a more quality fashion at altitude by planes or by satellites. So if this is a impact anomaly, it is the largest by far. I mean, the Bengui is really large, but this is huge. You see these four states here, quite notable. And what's also interesting about this is that this impact anomaly, potential impact anomaly, is located in the states that often report unusual things happening. In Arizona, there's Sedona. A lot of people think this is an energy vortex. You see that is located right in that zone. Also, like Utah has Skinwalker Ranch, and in general, just interesting energies there. So this remnant magnetization and this magnetic anomaly of North America could perhaps be related to some of these unusual things that people have been discussing for centuries in North America, going back to Native Americans and now in modern times. And there's so much evidence for that. Just look into, let's say, Skinwalker Ranch or Sedona Energy Vortex if you want to learn a little bit more about those. But if we just look at the magnetic field data, we do see this double ring structure pretty nicely and this central magnetic anomaly there. So this could be a very large impact. If you know anything about this, please leave a comment in the video comment box. I would like to learn about that, but this is something that I just saw in the data that I wanted to present to you. We also have more typical magnetic anomalies found in North America, like the Temagami magnetic anomaly. This is found in Ontario, Canada, and we see here that it has very, very notable magnetic flux. The peak is over 9,000 plus nanotesla, and it is very, very large. So this is actually located right next to the Sudbury Igneous Complex, one of the largest mining camps in the world. And this Temagami anomaly is a pretty long period magnetic anomaly, which means that's buried at least 1 to 3 miles down. So it may be difficult to mine, but a lot of people are now starting to look into this because this could be a very, very rich mineral deposit. 12 miles wide, 36 miles long, and it's an anomaly found by magnetic anti-gravity survey. So again, it's that combination of methods that really gives us confidence in the fact that this is something very, very significant geologically. Bears a striking resemblance to the Sudbury structure. It's located right next to it, of course. You can see just how, they're like twins almost. And its peak magnetic intensity is greater than 10,000 nanotesla. So again, like if you're here on this part of Earth's surface, the magnetic field is going to be significantly different than it would be on other parts of the planet, where typically the magnetic surface anomaly makes up less than 1% of the magnetic field. But here it's a 10,000 nanotesla difference from normal. So when you see a total magnetic field map for the Earth, this will all get rounded out and smoothed out, but there is tremendous variability in Earth's magnetic field, specifically in these spots that register these very strong magnetic anomalies. So these are distributed across the surface of the planet. Some of them are very large, like we looked at. Some of them are smaller, like this one. Still, this is 12 by 36 miles, so still quite large. But for example, North America, that entire craton is a magnetic anomaly. So that whole area is very, very large and alters Earth's magnetic field with remnant magnetization from Earth's prior magnetic field. So Earth's magnetic field, when it's passing up through the mantle, is then altered and changed by that remnant magnetization that the North American craton holds, or any little magnetic anomaly holds. And we also see that dynamic in Europe. So we have a very interesting juxtaposition of magnetic intensity in Europe, and let's look at that now. We have a surface magnetic anomaly map for Central and Eastern Europe here. We see the Black Sea, there's Crimea to get yourself situated in this map. You'll notice the extreme magnetic intensity of Eastern Europe, and this dividing line there separates Eastern Europe from Central Europe. Specifically, this is Poland and Romania. They have this magnetic anomaly cut right through the center of them. So in the west of Poland and Romania, the magnetic field is weaker, and then to the east and into Ukraine and Russia is much, much stronger. Also very, very strong in the Baltics and into Sweden and Denmark. Extreme magnetic anomalies found in that area. And so let's look at a few different maps that describe why we see this very large magnetic anomaly in Central and Eastern Europe. Here are 6 different maps which help us to understand this extreme magnetic anomaly which we find in Central and Eastern Europe. We have a magnetic data map from 5 kilometers up, another one at 100, a third one at 350 kilometers above the surface, and then a model at 350 kilometers up. We also have a heat flow map and a depth to MOHO, which is the crust to mantle transition zone map right here. And so this tells a complex geologic story. We'll start with this map. what you'll see here is that the depth of the MOHO is quite a bit less in Central and Western Europe than it is in Eastern and Northern Europe. So effectively, Western Europe has a continental crust that's about 10 to 15 kilometers thick, maybe a little bit less. And then right here in this transition, you get the continental crust increasing to about 50 to 55 kilometers thick. So there's a really big transition in continental crust thickness and depth. Eastern Europe has these really deep geologic roots, you could say, and this alters the heat flow. There's higher heat flow here in Western Europe, and then you get very low heat flow there because this is much older geologic material. So there's more remnant magnetization here. Earth's magnetic field was stronger in the past. That's what the geologic evidence suggests. So there is stronger remnant magnetization, and we see that very clearly with these maps here. At 5 kilometers, we see some of the short wavelength magnetic anomalies, but then as you move up, those get smoothed out, and you see the long wavelength magnetic anomalies appear. And at 350 kilometers, you really see this dipole form. So very nice dipole between the large block that has that strong remnant magnetization and then the block that has the lower remnant magnetization. Now, another interesting thing here is that if we look at the heat flow data, we see this big increase in heat flow in Italy. If anyone knows what that is, then you won't be surprised, but that is Campi Flegrei. This is a super volcano. This is a hot spot. So here in Italy, we have the mantle upwelling and creating this increase in heat flow. And if you look at this, just an interesting note, if you look at this hot spot in Campi Flegrei, you'll notice that's bounded in between these parts of Europe that have deep, deep roots. So you have the Alps there, and then also you have this depth of MOHO transition that is deeper down, surrounding Campi Flegrei there, and then there's our Eastern Europe, thick geologic continental crust there. So this Campi Flegrei, this mantle plume, is adding a bunch of mantle material and igneous material to the underside of this thin crust there. It's accreting it to the bottom. And of course, every now and then it explodes. Here we can see the explosion that was at Vesuvius and just estimate a model of what that looked like. So Campi Flegrei can really, really erupt at times. I've actually been there. I was there for Secrets Underground in 2017. Up here at the top of Mount Vesuvius, that's one of the highest geophysical measuring stations here at Mount Vesuvius. And there's the caldera behind me. Incredible. Look at that. Absolutely unbelievable. And then there's Naples. But you can see how these types of dynamics alter the magnetic field, because we have those deep roots, those thicker continental crusts, they have more remnant magnetization, and we can see that very clearly with our magnetic maps here, specifically also with our higher elevation ones, and we get this really nice dipole. So people living in this part of Europe, Central and Western Europe, are receiving less remnant magnetization than people living in Eastern Europe here. So Earth's magnetic field is able to pass through that part of the continental crust easier. And then in Eastern Europe, Earth's magnetic field still passes through the crust, but it is altered more by the remnant magnetization from the deep geologic past. So this is, hundreds of millions of years ago. It's hard to get an exact date, but you can look at the surface geology. It's hundreds and hundreds of millions of years. And this remnant magnetization was imbued into those rocks. So a lot of interesting things happening in Europe, and these magnetic anomalies tell us this story, as do a few other geophysical data sets like this depth of MOHO one and also this heat flow map. Surface magnetic anomalies are just one aspect of Earth's magnetic field, and I have a Earth's magnetic field master guide available for you. If you wish to learn more about Earth's magnetic field in a very comprehensive manner, this is a 2-hour lecture. These are the topics under discussion. We start at the core and the geodynamo, also georeactor theory, look at field strength, how it's altered over time, talk about the plasmasphere storms, power line harmonic resonance pulsations, different seasonal changes like the Russell-McFerrin effect, geomagnetic jerks, which occur on a yearly 2, 3, 4 time scale, and also we'll examine the movement of the North Magnetic Pole. We talk about geomagnetic excursions and reversals, something that there's a lot of misinformation out there right now about. So we look at the best available scientific evidence, and we also look at geologic history so we can get a better sense of how Earth's magnetic field does change over time, both in the human time scale and in the geologic time scale. So we look at this very comprehensively, and these magnetic anomalies are just one way of understanding Earth's magnetic field, but there is so much more. So if you wish to get access to this guide, you can join my channel as a special member for $5.99 a month, or you can get this guide as a one-off on Gumroad for $5.95, link in the video description. I hope you enjoyed this video on magnetic anomalies. I looked at the main magnetic anomalies and then also some other unusual features like the Richat structure, how that's located next to a magnetic anomaly, that potentially very large magnetic impact anomaly located in the 4-state area. And if you have suggestions for other things for me to look into, please leave a comment down below. I read all the comments. I thank you for all your support. And in general, I had a lot of fun making this video. You know, our Earth is a very amazing, wonderful place that we know so little about. So if you'd like to join me on my exploration of the Earth and of how energy affects the planet, how energy affects us, then you can subscribe to my channel. I hope to see you all here. Please share this video with a friend who's interested in geology and geophysics, and I'll see you all in the next video. Thanks so much, and have a great day.